This module is about a concept called the distribution of sample means. This module will likely challenge you in a way that the previous modules have not. I strongly recommend that if you get confused or lost, pause the video, rewind a little, and try again. This will probably take a little bit of time to understand. It will take a great deal of cognitive attention and effort. It is not a simple idea, but I will do my very best to explain it in clear terms that you cannot misunderstand. Now, before we begin, please have your unit normal table ready. Remember that's table B.1 that we have been using in the previous module. Just get out your printed copy of that and please keep it with you because we'll need to consult it later in the module. Before I even change from the title slide to slide 1, I want to just take a moment and have you work through cognitively what this title means. The distribution means, of course, a dispersion of scores, the way that a set of scores is distributed. Recall that we have looked at normal distributions. We've looked at distributions that are skewed and distributions that are uniform. This is the shape of a set of scores. We are going to be talking about a particular distribution that's made up not of scores, but instead of sample means. Now, if you think about that for a minute, you'll recall that a sample mean is taken from the population. When you draw a sample from a population of a certain size, if you compute the mean of that sample, that mean is intended to reflect the population. If we have a distribution of sample means, that means that we have computed the average of many samples and shown them in a distribution. I'm going to illustrate that for you later in the presentation, but I just wanted here at the outset to prepare you mentally for what it is we're going to be working on today. As you know, the location of a score in a sample or in a population can be represented with a z-score. You recall from our previous module that a z-score is composed of two parts, the sign and the magnitude, and that together represents whether it falls above or below the mean and how far above or below the mean. But researchers typically want to study entire samples rather than just single scores because samples provide an estimate of the population. Remember, in research, we're trying to use many individuals to guess what the entire population thinks, does, believes. Therefore, our goal is to learn how to transform a sample mean into a z-score. Now, you would think that would be very straightforward, but it ends up getting pretty complex. I'm going to shift back and recall from your memory a couple of days or weeks ago that a concept we covered early on, I think this was from the first module, is sampling error. You'll remember from this chart that sampling error is the natural discrepancy or the amount of error or the difference between a sample statistic and its corresponding population parameter. Recall that if you have a population of 1,000 college students, the average of that population, say in this example 21.3 years, will be approximated by each sample you take from the population, but each sample average will not perfectly reflect the population average. No two samples will be alike, and no sample will perfectly exactly yield the value of 21.3 years as the average age. Similarly, IQ will be different, and the percentage of female and male will be different from the population in every sample you take. That difference is sampling error. Remember, the principle here is that samples are variable. Two samples are almost never identical. Distributions in earlier chapters were distributions of scores from samples or from populations. But now we're going to use a distribution of sample means. This is the collection of sample means for all the possible random samples of a particular size that can be obtained from a population. In simpler English, I'll say that if you were to take all the possible samples of some size from a population and compute the mean of each one and plot them in a distribution, you would get this thing that's called a distribution of sample means. Sometimes this distribution of sample means is also called a sampling distribution. I will refer to it by both names as we go throughout the module because they are synonymous in my mind, and I don't always have cognitive control over which word I'm using. You will hear them among statisticians referred to equivalently, interchangeably, and so I need you to know that they're both the same thing. The distribution of sample means is also called a sampling distribution. Okay, we have seen this website before. I'm going to navigate back there once more. Okay, so you remember when we used this website before that the parent population is indicated at the very top and that we can draw samples. Let's start with samples of a sample size 5, and we can draw them from the population. This is 1, 2, 3, 4, 5 scores, and we compute the mean of the 5 scores, and we plot it here. If we're taking a sample from the population, we hope that the sample mean will be reflective of the population mean. The population mean here is 16. You can know that because this says mean equals 16, and this ranges from 0 to 32. This is halfway between the two. It's 16. This sample mean down here looks to be about 18, maybe 19. This sample mean is not exactly the same as the population mean. Why? Because of sampling error. No individual sample, or very few individual samples, will have a mean exactly the same as the population mean. If I animate another sample, drawing 1, 2, 3, 4, 5 scores from the population, and compute their mean and plot it down here, you'll see that this mean also is not exactly the same as the mean of the population. This is a mean of, say, 14. If I draw another set of 5 scores and I compute their mean and plot it down here, it will have a mean of, say, 15. And if I do that over and over and over again, tons and tons and tons of times, say 100,000 times, and plotted each mean from each of the samples of 5 scores, that would yield for me a distribution of means, a distribution of sample means. This distribution of sample means reflects the population in a couple of ways. You can see here that the mean of this sampling distribution is 16, and the mean of the parent population is also 16. So the average of all of the sample means approximates the population mean. Each individual sample is not exactly the same as the population, but on average, if we take a lot of samples, usually on average, they will approximate the population mean. Also, you should note that the pile of sample means here is a normal distribution. Interestingly, though, the shape of the normal distribution will continue to be reflected even if the parent population is not a normal distribution. So let's change this from being normal to being skewed. If the parent population has a positive skew here, where the tail extends far to the right, and we continue to draw samples, say, of 16, and we compute the sample mean for each of these samples, and we plot them down below, eventually, if we do this enough times over, and every time we draw a sample of 16, we compute the average and we plot it down below, and we do that over and over and over again, say 100,000 times, eventually we will yield a population distribution of sample means. And that distribution of sample means will be normal shaped even though the parent population was skewed. That is an important principle. Logically, also, we should recognize that every sample mean is not exactly the same as the population mean, but on average, they do come out to be equivalent to the population mean, and usually, even if they're not the population mean, they are close to the population mean. None of our samples of 16 fell way out here, estimating the population mean at, say, 28 or something like that. Most of them, if the population has an average of 8, most of the sample means had an average that was close to 8. Some of them were here at 9, some of them here at 7, 6, or 5, but most of them were very close to 8. Not exactly 8 because of sampling error, but they were close to 8. Now we're going to take a break from this and go back to our presentation. And I'm going to remind you of a couple of things we just learned. The sample means in that blue distribution piled up around the population mean. Not all of them were exactly the same as the population mean, but if you sample over and over and over and over again, most of them are pretty close. Sometimes they're far away from the population mean. For instance, if the population mean were 8, some of the sample means were as low as 4 or 3, but that's not a very good representation. It's still much closer than, say, negative 1,000, but some of them are going to be a little further away from the population mean than others, but most of them are going to be very close. The pile of sample means forms a normal shape distribution, even if the parent population is not normal shaped. Logically, a large sample should be a better representation than small sample, so the larger the sample size, the closer the sample means are to the population. In order to illustrate that last point, I'll return to our online representation, and I'll show you that if we have small samples of, say, just 2, and we compute from this sample of 2 the average, and this sample of 2 the average, and this sample of 2 the average, and we plot all of these down here, and we do it 100,000 times, the distribution is very, very, very wide. Why is that? Because a sample of 2 is not very representative of the population. Imagine for a moment that you wanted to guess who most Americans would vote for the next president of the United States. If you just randomly sampled 2 Americans, do you think you would have any confidence at all that your guess from the average of those 2 people would represent the actual average vote of all Americans generally? Heavens no, that would be absurd. Instead, you have to collect samples that are much larger in order to represent the whole population. And so, if we increase our sample size in this illustration from 2 to, say, 10, then you'll see that after 100,000 samples and computing the mean of each one and plotting it down here in the distribution of sample means, you'll see a much skinnier distribution. And as you increase the size of that up to, say, 25, it will continue to get skinnier and skinnier. The reason why this is because each sample mean is trying to reflect the population mean. But if you have larger samples, you can trust that those samples are going to better reflect the population. Remember, if you were to try and trust a sample of Americans trying to guess what president would be elected for the next president, you would not want to draw a sample of even 20 people or 50 people. You would want a sample of maybe 1,000 people that would better reflect the whole distribution of opinions across all the different states and areas and worldviews that exist in the country. You would want large samples to accurately reflect the population. And the principle here that I'm showing is the larger your sample, the better it will reflect the population. So that each of these sample means down here, because they have many scores in the sample, each of these sample means better reflect, they're closer to this average of 8. That is the population average. I want to walk you through another example. This example here is a very small population of just 4 scores. You can see them plotted here as 2, 4, 6, and 8. The mean of these scores is 5, right in the center. If you add them up and divide by 4, you can see for yourself that the mean is 5. If we were to draw samples with an n of 2, just very small samples, over and over again, that would look something like this. The first sample, remember this is random sampling, called independent random sampling, which means that we're replacing the scores after every draw. So in the first sample, we might draw the 2, and then replace the 2 and draw it again. So the first score would be 2, and the second score would be 2. If we computed the average of those two, it would be 2. The second sample might be if we draw the 2 and replace the 2 and then draw the 4. We could have 2 and 4, the average of which is 3. And if we kept drawing samples, 2 and 6, 2 and 8, 4 and 2, 4 and 4, 4 and 6, 4 and 8, etc., and we computed the average of each one of those samples, and we plotted them in a distribution graph, it would look like this. Interesting that, again, it forms a normal distribution shape, the mean of which is 5. This is a distribution of sample means from a population that was very small and yet still reflects the shape of a normal distribution. So again, there are some things you should have noticed in that process. The sample means pile up around the population mean. In fact, the mean of the sampling distributions is the mean of the population. Going back, you see the mean of the population was 5, and the mean of the distribution of sampling means is also 5. Most of the scores of the sample means are very close to 5. Some are 4, 3, a few are further away like 2 or 8, but most of them are very close to 5, between like 4 and 6. Some of them are exactly 5, but the point is they're lumping around 5. They're very close to 5. Not all of them are exactly the same as the population mean, but if you sample over and over again, most of them are pretty close. And finally, the pile of sample means forms a normal shape distribution. Now, the distribution of sample means is almost perfectly normal in either of two conditions. We've already demonstrated how these work, but I just want to make it very clear that it's even though the distribution of sample means like this ends up having a normal shape, much more normal than the population, it can still be somewhat skewed, and it will be more normal if, first, the population from which the samples are selected is a normal distribution. So, if the parent population is normal, then the sample distribution will be normal too, no matter the sample size. Whether it's 2 or 5 or 25 or however many are in your sample, the sampling distribution will be normally shaped if the population is normally shaped. But even if you have a skewed sample, a skewed parent population up here, if the number of scores in each sample is relatively large, at least 30, then your distribution of sample means will still be normally shaped, even if your parent population is skewed. I will exit the presentation once more, return to our online illustration and show you that if the parent population is skewed and we have very small samples like 2, and we take the average of 2 over and over again and plot them all, and we do that 100,000 times, we will get a sampling distribution that is more normal than the population, but still skewed. You can see this tail out here to the right. It's more skewed. It's still a little bit skewed. But the bigger our sample size, the less skewed it gets. You can see this is less skewed than it was when it was 2. Scores of samples of 10, less skewed still. And as we increase the sample size up to about 30, it only lets me go up to 25, but approximating 30, this gets more and more normally shaped. So, returning to the principles we should have noticed, you will see that the number of scores in each sample, if they're relatively large, at least 30, then the distribution of sample means will be normal, even if the parent population is not normal. We have this thing called the central limit theorem. A theorem is a rule that's not obvious on its own, not intuitive, but can be shown to be true through a chain of logic. So this central limit theorem is a rule about the central tendency of the sampling distribution. Quote, for any population with a mean of mu and a standard deviation of sigma, the distribution of sample means for a sample size of n will have a mean of mu and a standard deviation of sigma over the square root of n, and will approach a normal distribution as n approaches infinity. Okay, I know that sounded like a foreign language, so I'm going to break it down a little. If we have a population that has a mean of mu, like here, it's the mean of 16, and the standard deviation of sigma, in this case it's 5, the distribution of sample means down here for a sample size of n, which in this case is 5, will end up having a mean the same as the population mean of mu. So you can see here the mean of the sampling distribution is the same as the mean of the population. So the mean of the sampling distribution mu is the same as the mean of the population mu. But the standard deviation of the sampling distribution is not going to be the same as the standard deviation of the population. It's not going to be sigma. It's going to be sigma divided by the square root of n. So this standard deviation down here, which is indicated as 2.24, is not going to be the same as 5. It's going to be the same as 5 divided by the square root of 5. That's 2.24. And it will approach a normal distribution as n approaches infinity, which is what we just said on the last slide, meaning as you increase the sample size, larger and larger, approaching infinity, at least 30, but as you get larger, more and more normal, this distribution will become more and more normal shaped the bigger your sample gets as you approach infinity. So, I was originally going to re-demonstrate this using the online example, but I think I've just explained it well enough using this this screenshot from it. But if you want to go online and kind of play around with it, you have the URL, and you're more than welcome to go and explore and try to replicate this central limit theorem. The next concept that we need to learn is the expected value of the mean. The mean of the distribution of sample means, remember this is the distribution of sample means, and this is the mean of it. The mean of the distribution of sample means is indicated by the statistical symbol mu sub m. So I'm going to put it down here as mu sub m. And it has a value that's equal to the mean of the population of scores, mu, which is indicated here as mu. So this mu sub m is equal to mu, the population mean. The mean of the distribution of sample means is called the, quote, expected value of the mean. So this right here is read out loud as expected value of the mean. Remember, in Module 2, we mentioned that the mean is an unbiased statistic because of this fact, that the expected value of the mean is equal to the mean. So because on average, the expected value of the mean is equal to mu, we can say that that computing the mean is an unbiased statistic. Whereas if we compute the standard deviation, it is not equal to the population standard deviation unless we make a correction. So the standard deviation is a biased statistic. The next concept we need to talk about is the standard error of the mean. Variability of a distribution of scores is measured by the standard deviation. You'll recall that from a previous module where we learned that the variability, the differences in scores, is measured by the standard deviation. That if you have a distribution of scores and you want to know how far apart they generally are, how far apart each score falls away from the mean of that sample or that population, that can be defined as the standard deviation, the typical deviation of scores away from the mean. Variability of a distribution of sample means is measured by the standard deviation of the sample means and is called the standard error of the mean and written as sigma sub m. So, variability of a distribution of scores is measured by the standard deviation, as indicated here. The red bar shows how far the standard deviation is. In the population here, it's 5 points. And the variability of a distribution of sample means here is measured by the standard deviation of the sample means, which is 2.24, and is called the standard error of the mean. It's written sigma sub m. So this red bar, which is shorter than the parent population red bar, is indicated as sigma sub m. In journal articles or other textbooks, the standard error of the mean might be identified as standard error or SE or SEM. Those are all abbreviations for it, but this idea is that the standard deviation of the sample means is always shorter than, always lower than the standard deviation of the population. And it's shorter or lower by a reliable, trustworthy amount, which is, as we saw in the central limit theorem, sigma divided by the square root of n. So if you want to compute the standard deviation of this distribution of sample means, you would do 5, the sigma, divided by the square root of n, 5, and that would give you the standard deviation of this sampling distribution, 2.24. Now remember that the standard deviation measures how far on average the scores deviate from the mean. If you have scores in a sample, these individual scores are not equal to the mean of this sample is 16, and the scores are typically about 2 points away from the mean. Here, this is 1 point away, this one is 2 points away, this one is also 2 points away, this is 1 point away, this is 1 point away, this is 3 points away. You can see that the standard distance away in this sample here is 2, and the mean is 16. We indicate, as you recall, the standard deviation as an italicized little s and the mean of the sample as an italicized m. If you were to compute the standard error of the mean, that would provide a measure of the average distance between the sample mean and the population mean mu. So if this were a population mean instead of a sample mean, say this was mu and this was sigma, then the standard error of the mean would be to take sample after sample after sample from this population and compute a sampling distribution down here, and the mean of which would be the same as the population mean. Then we would indicate the standard error of the mean as a distance between each sample mean and the population mean. So typically, how far away do sample means in this distribution fall away from the population mean of 16? The answer to that question is 1.63. That's how far away they are, typically on average. So like this sample mean right here falls 1 point away from the population mean. It's 15, the population mean is 16. This score over here falls 2 points away. This score over here falls 3 points away. But on average, if I were to compute all of them, they would typically fall 1.63 units away from the population mean of 16. But because the standard error of the mean is equal to the mean, the standard error also provides a measure of how much distance to expect between any individual sample mean and the population mean. So if we took this sample, and this was the only sample from the population that we drew, and we computed this mean alone, and we wanted to know how close we were to the population mean of 16 on average, we might say this sample right here is probably somewhere around 1.63 units away from the population mean. If we didn't know how far away it was from the mean, if it was higher or lower, we would say we think the population mean is 15 based on our sample. But it might be 1.63 units higher, or it might be 1.63 units lower, but we think it's somewhere around 15. And if we guessed that, and if we said it was maybe 1.63 units higher or lower, then we would be right. It is 1.63 units higher or lower. It's 16. It's 1 point higher. If we got this right here, if we got this sample and we computed the average and we said we think the population has an average of 14, but it might be somewhere between 1.63 units higher than that or 1.63 units lower, we wouldn't be exactly right because 1.63 units higher than 14 is 15.63. But even so, we would still be very close within that range of almost capturing the population mean. The standard error of the mean is, therefore, a very valuable measure because it specifies precisely how well a individual sample mean estimates its population mean. So we can use the standard error of the mean to guess how much standard error there is. We can use the standard error of the mean to say, in our sample, how far away we think the actual population mean is from the mean of the sample that we computed. Or in other words, you could try to figure out how wrong you are. You could try to figure out how far away your estimate is from reality. We're going to talk next about the standard error magnitude. The size of your standard error is determined by two factors. Or said another way, how well your sample is likely to represent the population mean depends on two factors. So recall that in the last slide we just were talking about the standard error, the distance between a sample mean and the population mean, on average how far away that sample mean might be from a population mean. It's going to depend on two things. The first thing is, the larger the sample size, the more probable it is that the sample mean will be close to the population mean. This is known as the law of large numbers. Just to give you, to repeat the example we used before, if you had a sample from the United States that was just 20 people, and you were trying to guess anything about the whole population of the United States, who they would vote for president, or how tall the average person is, or what their IQ is, or anything about anybody, then you probably couldn't say very much about the population because your sample would be pretty small. But if you had a sample size that was larger, like say 500 people or 1,000 people, then you could with greater confidence compute what you think is probably very close to the population mean of all the people in the United States. So the larger the sample size, the more confident you can be, the more probable it is that the sample mean that you've computed from your sample will be close to the actual real population mean. The second characteristic that will help you determine whether your standard error is high or low, whether you have a lot of incorrectness in your estimation, is the population variance. The less population variance there is, the more probable it is that the sample mean will be close to the population mean. I'm going to take a moment to go back again to our online example and show you that if we keep the size of the samples constant at n equals 25, and we compute 100,000 means from this parent population that is pretty widespread, your sampling distribution will be skinny. But if you want it even skinnier still, just restrict the size of your parent population. If your parent population looks very thin, then your sampling distribution will be even thinner. After 100,000, almost every single one will perfectly reflect the population mean. If I use, I'll walk through this example again. If we go back to a widespread population and we use an n of 5 and we do 100,000 of those, your sampling distribution will be much wider than if you have a parent population that is somewhat thinner and you want to compute, you still keep the sample of n equals 5, but your sampling distribution here in this case has a much more restricted distance than it did before when the parent population was wider. So going back to our presentation, you'll be able to make better sense of this point now. If the population variance, the spread of the scores, how wide that distribution is, if there's less population variance, then you're more likely to be able to estimate the population mean from the sample mean. The sample mean is going to be close to the population mean if the population variance is restricted, if it's small. This is a graph that illustrates the relationship between standard error and sample size. You'll notice that as the sample size increases here on the x-axis, that's n here, the sample size, there's less error between the sample mean and the population mean. There's less error. So this right here is a measure of standard error. If you have one score in each sample, that is a very, very poor sample from a population. Imagine if you wanted to guess the voting patterns of all the people in the United States based on one person. That would be crazy. You would have a ton of error. You would have the most possible error. So in this example, if you have an n of 1, then you would have a huge amount of error. But if you increase your sample size to 4 or 9 or 16, 25, the higher your sample gets, the less error you have. That is to say, you will get better and better estimates of the population mean the bigger your sample is. You'll note from this graph that researchers can substantially reduce their error by increasing their sample size here at the beginning of the graph. But you've got an elbow somewhere around here that seems to indicate up to around n of 30, you can keep adding people to your sample and keep reducing the amount of error incrementally. But samples larger than 30 don't really do much to increase how well the samples represent the population. If you have about 30 people, that's right here, 30 people in your sample, if you add 6 more, you will decrease your sampling error just a tiny bit, just from here to here. That's hardly any. And if you add another, nearly 15, you will decrease your standard error just a tiny bit, and add another 15, a tiny bit more. And if you eventually add just 100 or 1,000 people, you will still have some degree of sampling error. You just have to recognize that 30 is an optimal size for maximizing the reduction of standard error with the fewest number of people possible. So in statistics, you will often hear that when you have a sample of around 30, you can trust that your sampling error is reasonably low and that your sampling distribution is reasonably tight and normally distributed. The next principle we want to talk about is probability and the distribution of sample means. This is a combination of the material we've covered so far, the distribution of sample means, with the principles of probability that we talked about in the last module. The primary use of the distribution of sample means that we've been talking about so far is to find the probability associated with any particular sample mean. For example, consider the population of SAT scores that has a mean of 500 and a standard deviation of 100. We could ask ourselves, what is the probability that the sample mean will be greater than 540? In this example, we can't construct the sampling distribution, but we know what it should look like based on the central limit theorem. Now, the reason why we can't construct the whole sampling distribution is because we can't actually draw sample after sample after sample after sample after sample after sample from all the people in the population and keep computing the average of their SAT scores in those samples and create some sampling distribution. But theoretically, using the computer modeling that we did earlier and the principles of the central limit theorem, we should be able to draw out what we think it will look like. So we know that the distribution is going to be normal because the population is normal. And we know that it's going to have a mean of 500 because the population mean is 500. And the sampling distribution always has the same mean as the population itself. And if we have a sample of, say, 25, then the distribution has a standard error of 20. Why? Because the standard error of the mean is equal to sigma over the square root of n. It's equal to the population's standard deviation over the square root of the sample size. So if we take the standard deviation of the population, 100, and we plug that into the equation, and we divide it by the square root of n, if the n is 25, and we plug that into our equation, then we could say square root of 25 is 5, and 100 divided by 5 is 20. So the standard error of the mean is 20. If we draft out the population then, the sampling distribution then, the distribution would be normal shaped, have a mean of 500, and a standard deviation or a standard error of 20. That looks like this. Normal distribution, mean of 500, standard error of the mean of 20. And we could ask ourselves this question: what is the probability that the sample mean will be greater than 540? Marking off this score right here of 540, shading in this tail to indicate all the sample means that will be greater than 540. We might ask ourselves now, because we are interested in sample means greater than 540, we use a z-score to locate the position of this value. So what is the z-score? We have to use the standard deviation of the sampling distribution, 20, not the standard deviation of the SAT scores, 100. We have to use this standard deviation, not the standard deviation of the original population. So, if we compute the z-score that's associated with 540 using this standard deviation, you should be able to just do that in your head, because if the standard deviation is 20 and the score that we're interested in is 540, which is 2040 above the mean, then we should be able to intuit that the z-score associated with 540 is 2. Since this sampling distribution is of normal shape, we can use the unit normal table to discover the probability associated with a z of 2. So please pause the video, go to your table B.1, your unit normal table, and figure out what is the percentage of scores that is higher than a z of 2, which is equivalent to the score of 540. Percentage higher than a z of 2. Should have discovered that it was 2.28%. Therefore, it would be very unlikely to obtain a random sample of 25 people from the regular population with an average of SAT scores greater than 540 just by chance. If we gathered a sample of 25 people and we computed their SAT and it was higher than 540, it's possible that that was just by chance. 2% of the time that would happen. But if we gathered that and we had done some treatment in a research study, we could probably conclude that's a rare enough occurrence that whatever we did to them probably caused them to be up here in this distribution, rather than just having that be because of chance. We are now going to talk about computing a z-score for sample means. Essentially, this is the same as the z-scores that we used in the last module, but we're using new notation in the computation. Things that are the same about it is the sign of the z-score tells whether it's above or below the mean. The number, the magnitude, tells the distance from the mean in standard deviation units. In this case, it's actually standard error units. So the formula for sample means is very similar to the z-score for samples, for individual scores. So instead of x minus the mean over sigma, we have the mean of the sample minus the mean of the population divided by the standard error of the mean. So, to illustrate what's going on here, we might take a sample of 5 scores, compute their mean, and plot it here. Note that the mean of this sample is not the same as the mean of the population. This sample looks to have a mean of about 18 compared to the mean of the population at 16. But if we took this one sample and we imagined the rest of the sampling distribution as this, then we could say, where does this score fall within this sampling distribution? What is the z-score associated with it? Since this is a sample mean that came from those original 5 scores that were plotted up here, we have to plug this mean into the z-score formula and subtract it from the mean of the population, which is the same as the mean of the sampling distribution, and figure out how far away is that from the middle of the sampling distribution, and divide it by the standard error of the mean, which is the standard deviation of this distribution of sample means. So instead of using a score from a population, we're using a sample mean from a sampling distribution. But the principle is still the same. If we were to look at this individual sample mean here and say, what's its z-score likely to be? Since the standard deviation of this population, of this sampling distribution here, is reflected by the red line, you could say this falls just beyond that. If this is a z of 1 right here, and this is a z of 2 right here, this sample mean probably has a z of like 1.25 or something like that. And that would indicate to us that the interpretation of the z for a sample mean in a sampling distribution is the same as the interpretation of a z-score within a population. Let's walk through an example of what we can do once we know how to compute the z for a sampling distribution. With this information, it's also possible to make quantitative predictions about the kinds of samples that should be obtained from any population. So let's once again consider SAT scores that have a mean of 500 and a standard deviation of 100. This time, we're going to determine what kind of sample mean is likely to be obtained as the average SAT for a random sample of 25 students. Specifically, we determine the exact range of values that is expected for the sample mean 80% of the time. So we're trying to figure out if we capture the middle 80% of the distribution, the bulk of them, most of them, what kind of sample mean are we typically going to see 80% of the time? Let's draw it out. If we compute the sampling distribution, we will see here that the mean is 500, just like the population mean. But the standard deviation is not 100. Remember, it's sigma over the square root of n. And if our sample size is 25, then we have to take the square root of that. It's 5. The standard deviation of the population was 100, and we do 100 divided by 5. That sigma, the standard error of the mean equals 20. So this is our sampling distribution. If we try to figure out from this, what are the z-scores associated with this middle shaded 80%, those will be reflected down here. Please take a moment, pause your video, and look at your unit normal table to figure out what are the z-scores that have 10% in the tails or 40% between the z and the mean. You should have found that the z-scores associated with those two boundaries were negative and positive 1.28. Now, if you wanted to compute the scores associated with these z's to uncover these boxes here, you would have to use the formula on your formula sheet, that is x equals mu plus z times the standard deviation. In this case, we use the standard deviation of this distribution, which is 20, and we plug in the mean of this distribution, which is 500, and we use the z-scores that we just found, negative and positive 1.28, and we plug both positive and negative 1.28 into our formula, along with the mean and the standard deviation, and we compute both of these scores here as 474.4 and 525.6. Those are the scores that capture the middle 80%, and we can be 80% confident that if we draw a mean of a sample of SAT scores, that mean will be in the range here 80% of the time. We're 80% confident that the mean will fall within that range. Now I just want to review once more, back to the beginning of this presentation, the concept of standard error. Remember, there will usually be a discrepancy between a sample mean and the true population mean. If you have a population mean like this, the sample mean like this will not be the same as the population mean. This discrepancy is called sampling error. It's how wrong our samples are just because samples are not exactly the same as a population. The amount of sampling error varies across samples. This average of the sample is lower than this average of the sample. So this is actually a poorer representation of this population than this is, because 21.3 is much closer to 20.4 than it is to 19.8. So the amount of sampling error, the degree of difference between the mean of one sample compared to the population and the mean of another sample compared to the population is going to differ. It varies. And the variability among those different samples, the variability of sampling error, is measured by the standard error of the mean. So what we've been computing over and over again and demonstrating as sigma sub m, the standard error of the mean, is a reflection of the variability of sampling error, of how wrong we are. So this is an example of a typical distribution of sample means. To demonstrate some additional principles about error, I just want to remind you that this is a sampling distribution. That means each small box here represents one sample mean. It is not an individual score, it is a sample mean. And the mean of this sampling distribution is mu sub m. To reiterate, there will usually be some discrepancy between the sample mean and the population mean. This is known as sampling error. Only this column of samples had a mean that is exactly the same as the population mean. But most of the sample means, over here and over here, are relatively close to the population mean. However, some of the samples produce means that are out in the tails of the distribution, relatively far from the population mean. In other words, if we drew samples from the population and computed the average, they might fall far away from the population mean some small percentage of the time. So some samples will have smaller error, like this one right here has an error of just a couple of units. But sometimes our samples will have larger error. they will be far away from the population mean just by chance. The standard error provides a way of measuring the average or standard distance between a sample mean and the population mean. It's a typical distance. This standard error, remember, is reflected as the standard deviation of this sampling distribution. That standard deviation here, or the standard error, is a typical distance of how far away most of these sample means are from the population mean reflected here. Sometimes they're close, sometimes they're far, but on average they will be that distance right there, the standard distance, the standard error. So this is a way of measuring sampling error. It's a way of figuring out how wrong we are, how far apart our sample means typically are from our population mean. When we're displaying standard error of the mean, we usually use these bars that span a score above and below. So group A might have had like a score of 15, a mean of 15, but the standard error is some guess of the true distance where the population mean falls, above or below that guess of 15. And we draw it with bars like this to indicate that when we have an estimate of 15, that's just our sample, and we don't know exactly where the population mean is, but we're guessing it's somewhere in this range. It might be as low as 10 or as high as 20, but it's somewhere in that range, we think, because our standard error tells us that the typical distance of a sample mean from a population mean is that far. That is the standard error right there, either on the upper side or the lower side, and we draw the box on both. So you can see on a line graph we do the same thing. For every dot that is a group mean over a number of trials, we draw a bar, and that bar represents the standard error of the mean. We want to take a moment and look ahead to inferential statistics now, because, as I've said many times, the whole point of all this foundational material is to allow us the opportunity to run these inferential statistics that draw inferences about the population. So, inferential statistics use sample data to draw general conclusions about populations. We draw, say, 100 people from the population of the United States, and we try to draw a general conclusion, guessing what kind of characteristics that population of the United States has. Sample information is not a perfectly accurate reflection of its population. That's the principle we've been talking about many times, called sampling error. When you draw a sample, the mean is never going to be exactly the same as the population. And the differences between the sample and the population introduce some degree of uncertainty into the inferential process. We can make guesses from our samples about the population, but we don't know how accurate our guesses are. There's some uncertainty there. So there are statistical techniques that use probabilities to draw inferences from sample data to say how likely we are to get samples of a certain size, with means of a certain size, given the characteristics of the sample that we drew, sample size and things like that. So let's imagine this conceptualization of a research study here. This is the same research study that we've been using to illustrate a lot of different things. We've got a population of rats with a normal weight, mean of normal distribution with a mean weight of 400 grams and a standard deviation of 20 grams. If we draw a sample of 25 rats and we give them some treatment, our treated sample might be different from the population, but we need to know how different. Imagine that you have this population of rats. If the standard deviation of the population is 20, then the sampling distribution would also have a mean of 400, but the standard error of the mean would be something different. Take a moment, pause the video, and try to figure out what that would be. Use your formula sheet, and remember that the formula for standard error of the mean uses the standard deviation of the population divided by something. Figure out what the standard the sampling distribution in this example would look like. You should have remembered that from the last slide we drew samples of 25, and since the standard error of the mean is equal to sigma over the square root of n, we plug these things in: sigma, or the standard deviation here, divided by the square root of n, which is 25, and we would carry that formula through to result in a sampling error of 4. We can use this information to calculate the middle 95% of the sample means in the sampling distribution. So if we draw the sampling distribution out, it would have a mean of 400, just like the population, but instead of a standard deviation of 20, it would be skinnier. It would only have a standard deviation of 4. And then, if we said the middle 95% is bounded by these z-scores of positive and negative 1.96, you could verify that if you want in your unit normal table, but you'll see that these bind the middle 95%. We could compute what these scores are equivalent to, and we would say that most samples, 95%, would fall between a weight of 392 to 407. We can imagine that each of the boxes here represent one sample mean in this sampling distribution. What if we drew a sample and at the end of the study, this is where it fell in the sampling distribution? Do you think the growth hormone worked? Hopefully you said probably not. It probably didn't do anything at all to make any difference in the size of the rats. In fact, the rats are slightly smaller than the average. So if we drew a sample of 25 rats and we computed their average weight as slightly below 400, then we might say this sample right here suggests the growth hormone didn't make them heavier. What if the sample ended up here instead? What if the sample mean of 25 had an average that fell out here? Do you think the growth hormone worked? Hopefully you said yes, because this sample mean falls outside that range from 392 to 407. This sample mean is more extreme, much more rare that we might find it by chance. Is it possible that we could randomly draw 25 rats that weighed this much? Yes. But how often would that happen? Less than like 2.5% of the time. So before we conclude this presentation, I want you to walk through an example. Given that the average IQ of adults in America is 100, with a standard deviation of 15, if we were to draw 25 folks at random from the population of the United States, about how far on average should we expect their mean of the sample to fall from the population mean? Please pause your video, think critically about this, and use what we've learned so far to figure out the answer to this question. Hopefully you drew a population distribution first to indicate that the mean of the population of IQ scores is 100 with a standard deviation of 15. Perhaps then you drew a sampling distribution underneath it with a mean of 100, and you're trying to figure out how far on average do sample means in this distribution fall away from the population mean of 100. That is reflected by the standard error of the mean. To compute the standard error, remember that the formula is sigma over the square root of n. The standard deviation of the population is 15, so we plug that in. The n size was 25 folks. We put that here. The square root of 25 is 5. 15 divided by 5 is 3. So the standard error of the mean is equal to 3. That is the distance that you can expect for any sample that we draw from the population to diverge from the actual mean of 100. So we might draw this sample here, and it might be about 3 away from 100. We might draw this sample here, and it might be further than 3 away from 100. But on average, most of the sample means are only about 3 points away from the mean of 100. Some are further, some are closer, but on average, the typical distance away is about 3 points.